Okay, let's talk about a priority queue. Priority queue is the most important data structure. It organizes a collection of items and can always give us extreme value. There are many implementations. First of all, let's consider implement with an ordered array. With an ordered array, the extreme value is at the last index. However, in order to insert a new item, we need to move the items rightward in order to empty a new slot. For example, if we have a mini item, we want to add a new item in the middle, we have to move half mini items in order to empty a new slot. So on average, adding a new item, the cost is proportional to n. And another approach is use an unordered set. Adding a new item costs 1. However, in order to delete maximum, we need to read through the whole set in order to find the extreme value. And the cost is proportional to n. We want an algorithm with reasonable insertion cost and delete maximum cost. The natural tree can inspire us. It has branches to put more material on, and gravity also put emphasis on the root, which have the biggest diameter. Now let's have two definitions to extract the two successful factors of tree. Definition 1. Binary tree. A tree whose elements have at most 2 children is called a binary tree. Natural tree have many branches. We just need 2, which is simple, and also captured the essence. Definition 2. Heap order. The value of each node is smaller than or equal to the value of its parent. If we have this definition, we know at the bottom the node is bigger. When we go up, the node gets smaller and smaller. So a heap ordered binary tree extracted the essence of a natural tree. It is already a priority queue. Let's see how a heap ordered binary tree helps us. So in order to add a new item, we just have to add it to the tip. And the heap order might be violated. The child might be bigger than the parent. We can fix it by exchanging the parent node and the child node. At the worst scenario, we have to swim the new item from the tip to the root. The cost is not bigger than the height of the tree. And what is the height of the tree? If we have n element, the height of the tree is logN. So as we see the binary tree at each level, the node number doubles. So the total height of the tree is logN. So if we have a mini item, in order to add into an ordered array, we need to move half a mini item on average, but in order to add it into a heap ordered binary tree, we just have to do 20 move. So the height is 20, which is a big improvement. Now let's take a look at a delete maximum. We know the maximum value is at the root. So we take the root and we need to put something back. And we just grab an element from the tip and put at the root. Of course, the heap order is violated. We can fix it by exchanging the parent with a bigger one of the 2 children. And we can keep doing that until the heap order is restored. At the worst scenario, we have to sink an element from the root to the tip, and the number of moves will be no bigger than the height of the tree, which is logN. Again, if we have a mini item, the cost of deleteMax is no bigger than 20. So for a heap ordered binary tree, the insertion cost and the deleteMax cost both are logN. Now we have the idea. We need a program to realize this idea. And we can use an array to represent the heap ordered binary tree. Each index represents a node. And in order to get the parent node, we divide the current index by 2. In order to get the 2 child nodes, we multiply the current index by 2, and we add 1 in order to get the right child. For example, at index 3, the parent node is 1. There is a small trick. 3 divided by 2, we get 1, because in computer, integer division, we get the floor. So both 3 and 2 have the common child at index 1. They divided by 2 both yield 1. And the 2 children of index 3 is 6 and 7 accordingly. So now we can navigate up and down a heap ordered binary tree. Let's write the program. Now the max size of the binary, the priority queue. We need to add 1 because we don't want to use the first index. The first index, 0 multiply 2 divide 2, we go nowhere, so we don't want to use the first index. That's the reason we add 1. Also, we need the size of the heap. Next, let's write a convenient function. Because it's used often. Now let's write a swim so that we can move the element upward. Where k is not at the root. And the heap order is also violated. We exchange them. Each time we decrease the index. That's a swim. With a swim, the insert is just 1 step away. And we increase the heap size, and we put the item in. Now, the heap order might be violated, so we just have to fix it. That's insert. Now let's write the sync to move the item down. Where this is not the lost item, then we can calculate the left child, the index of the left child. And we also need to consider the right child. If the right child is bigger, we want to take the right child index instead. Now we want to exchange k with a bigger child, and at each term we want to increase the index. However, we need to break out from the loop if the heap order is not violated. Okay, with sync we can now implement deleteMax. So we know the value is at index 1. We just have to return it. However, we get a tree without the root, so we need to fix it. We exchange the root with and minus minus. Now heap order is violated. We fix it. We also decrease the heap size. Now the priority queue is finished. Let's test it. Oh, we forgot to implement the size, so public int size. Just have to return n for oh, let's don't do this. Let's do int I from array. Let's create a priority queue. Queue equal new priority queue. Okay, let's randomly insert some elements. Now, as long as queue is not empty, we call the deleteMax and we print it out. Okay, let's run the program. As you can see, we randomly insert items, and each time we get the maximum value. That's a priority queue. And the cost of the implementation is logN for insertion and logN for deletion.